Let's discuss what we mean by critical points in Calc 3. Well, critical points in Calc 3 are pretty much the same as critical points in Calc 1. Let me talk about that. When we talk about local extrema in Calc 1, we're talking about local maximums and local minimums. And generally, those can't happen in too many places. There might be a corner, a nice smooth thing. There might be another corner or something like that. But if we're talking about local maximums, we're talking about the points that are higher than any points close by. So for example, something like that, something like that. If this happens to be an endpoint, something like that. If we're talking about local mins, we're talking about points that are lower than any points that are close by. So something like that, and something like that, and something like that. Now in Calc 1, what we'll do is we'll say if you're at a local min or a local max, and the derivative exists, then the derivative must be 0. So if you're at a local extrema in Calc 1 and the derivative exists, if f prime exists, then f prime must be 0. If the derivative doesn't exist, then the derivative doesn't exist, right? So the whole point is that if you are in a local extrema in Calc 1, then either the derivative exists and it's 0, or the derivative doesn't exist. And you can see that would actually catch all of the local extrema on this example. And it actually will catch all the local extrema on any example. How much different is it in Calc 3? Well, we really don't have that many different kinds of maxes or mins here. I mean, so for example, we've had bowls that look like this. We've had cones that look like this. Everything where we've had a max or a min either was something like that, where it's nice and smooth, or this, where it's a corner. Now, let's actually draw another one just so I can have one that's upside down. All right, here we go, like this. Yay. Now let's just focus just at this one. What I want to do is say, if I'm at a maximum where the derivative, if I'm at a maximum and the partial derivatives exist, what can we say about the partial derivatives? Well, if I take a section parallel to the y-axis, I'm going to get something like this, and you can see the partial derivative in that direction would be 0. If we take a chop in the other direction, harder to draw, but it's not that miserable. If I go like that, right? If we draw a section parallel to the x-axis and take the partial derivative there, we can see that partial derivative is equal to 0. So this actually mirrors what happened in Calc 1. If you're at a local max or a local min where the partial derivatives exist, then both partials must be 0. If you're at a max or a minimum where one of the partials doesn't exist and one of the partials doesn't exist, we can draw this whole thing as a conclusion. Now let's make it better than this, I guess. If P is a local maximum or a local minimum, so we're going to say local extrema. That's all that means for F. Then one of two things has to happen. Well, either both partials are equal to 0. Well, we can say that in a single statement. If we take the gradient, remember what the gradient is, you take the partial with respect to x, you take the partial with respect to y, and you turn it into a vector. So that if both partials exist and you're at a local maximum or minimum, then the gradient must be the 0 vector, which means fx equals 0 and fy equals 0. If you're at a place with a corner, then the gradient doesn't exist. Does not exist. And those are our two options in Calc 3, just like they were our options in Calc 1. Just recapping. If we're going to be looking for local extrema, we're going to want to set partial x equals 0, partial y equals 0, and solve. If the partials don't exist, we're going to actually have to try to see what happens with fx and fy, and see if we can't still solve for the points where one of the partials or both of the partials doesn't exist, like here, where we have a corner. So that's the end of the analogies for Calc 1 to Calc 3.